Okay, welcome everyone for our first Tuesday and the real hybrid seminar, so half live. And Cynthia will teach us about log-concave polynomials.
Thanks very much for everyone to come. Please let me know if you can't hear or see something. I think Avi is going to keep an eye on the chat if you have questions in the chat.
Or shout them out. Even
better, just shout them out and we'll do our best. Yeah, so I want to talk about log-concave polynomials in theory and applications. This will be based on joint work with Nima Anari, Tikbi and Cheyenne Ogeskaran. It has some overlap with work of Peter Van Den and Jun Hu on Lorentzian polynomials. And apologies for any of you who came to my members seminar talk. There's going to be, a fair amount of overlap, but I thought it best to just start at the beginning. So this will probably be on the more theoretical side of the talks in this seminar. But the goal is going to be to study a class of polynomials. The goal for today, at least, will be to understand class, namely the log-concave polynomials, a class of polynomials these will be real polynomials with non-negative coefficients in variables x1 through xn, and I'm going to take them to be homogeneous of degree d. I'll go through the notation in a bit. So we're just going to try and understand a class of polynomials. And the reason one might want to do that in a discrete math computer science seminar is this can actually, it'll turn out that this can give you interesting inequalities on combinatorial objects. So interesting inequalities. I'll be fairly vague right now on combinatorial objects. And then from a computer science standpoint, one reason to do this is that if you associate to such polynomials discrete distributions, it turns out that they have nice properties with respect to sort of approximate sampling and approximate counting. So this should not make a huge amount of sense, but this class of polynomials we'll introduce is also nice from a sort of approximation algorithms standpoint. So enables approximate counting, sampling, from distributions given by the coefficients. So that's why you might be interested in a class of polynomials. Today I'm going to stay mostly on the theory side of this, and then another talk where I'll talk more about the applications. So hopefully you're okay with taking my word for it on this so far. I'm going to just start out by fixing some notation. Notation. So I'll be taking polynomial and variables, degree d. So this means I can write it as a real linear combination of binomials, which I'm just going to index C alpha for the real coefficient, which which I will often shorten as just C alpha x to the alpha. And we use this to denote polynomials that are homogeneous of degree d. So that means that the sum of all the exponents that appear. And two polynomials, I can record what monomials show up, which I'll call the support of a polynomial. So this would be a set of exponents that show up with non-zero coefficients. And I might also be interested in the Newton polytope. I can associate a polytope to such a polynomial, and it's just going to be the convex hull of the support. So just to be super explicit, so if I took x1 to the fourth, x5, x1 cubed, x cubed plus x2 to the fourth, nice homogeneous polynomial of degree 4, then its support color. So I have 4, 0, 3, 1, and 0, 4. That's its support, and the convex hull is just going to be this line segment. Since it's homogeneous, it's always going to lie in the hyperplane, sum of the coordinates equal to d. So I'm just going to save myself a dimension and draw 1d, the dimension down. Similarly, a slightly more interesting example, take the elementary symmetric polynomial of degree 2 and 4 variables. So sum all pairs ij between 1 and 4, and just the product of those variables. Then this is the Newton polytope. And in this case, the Newton polytope, the convex hull of all vectors. And I get a nice hockey. It's really in 4 space, because since it lies in a hyperplane, it's 3-dimensional polytope. The sun, be lazy and denote this. Use 1, 2 for E1 plus E2. And then just last piece of notation. So I use partial sub I to map the derivative with respect to the variable xi. Think of a monomial in these. The derivative with respect to the I variable, alpha I times, where alpha is the vector of non-negative integers. And I'll also be interested in directional derivatives. So just first, I take some vector v, the sum the n of the bi times the partial derivative.
So a question. Yeah, about the Newton polytope. It always amazed me that this object ignores completely the value of the coefficient. That still gives information about this polynomial. So any intuition at this level, maybe we'll see later, but any intuition why it should, given that you ignore the coefficient.
Yeah, I mean, I'll do a little bit with the Newton polytope, which may or may not help, but I think if you're keeping track of monomials, then what the Newton polytope does, one way to think about it, it keeps track of where the polynomial, how the polynomial interacts with the coordinate axes. So like, if you, I mean, the simplest example, if you don't have if you don't have a zero coefficient on the you don't have a constant coefficient, you evaluate to 0 at 0. But then if you start, removing more coefficients, that tells you that you vanish along coordinate subspaces.
So just using the non-negativity of the coefficient. So,
yeah, or the non-zeroness.
Yeah, so you're just,
so it's keeping track of how you interact, how the polynomial vanishes along the coordinate subspaces, and that's sort of invariant under a lot. You can do a lot to the coefficients now. That's the short version.
Isn't it also captured by the behavior of infinity?
Yeah. So 0 will, yeah. Exactly. So far we haven't done too much. Okay, so let's at least introduce the class of polynomials. So polynomial with non-negative real coefficients, homogeneous in degree t. I'm going to say is log-concave. So I'll be raising it LC on the positive orthant. If either it's identically 0, or so if it has non-negative coefficients and it's non-zero, then it defines a positive function. It takes positive values on the positive orthant, and so composing with log makes sense. What I want is that log of f as a function on the positive orthant is concave. And in fact, I'm going to want something slightly more. I'm going to say that f is completely log-concave.
The coefficients, positive, non-negative?
Non-negative, yeah.
Non-negative.
Yeah, so all of the coefficients that appear will be non-negative. It's completely log-concave. If not only f is log-concave, but whenever I take any directional derivatives with respect to vectors in the positive orthant, I get something log-concave. So for all choice of vectors, say v1s or vr in the positive orthant, to take all of those directional derivatives, I want for any number of vectors, I want the resulting polynomial to be log-concave. That's the class of polynomials that we're going to be looking at. And some of the motives, so one reason to look at such a thing is it actually contains a lot of nice examples, including, so by the generalized Brun-Minkowski theorem, if you take mixed volume polynomials, so you take volume x equals k1, kn, where ki is a convex body. Turns out that these have this property of being completely log-concave.
But first of all, it's a polynomial.
Not only, so there's a lot of theorems hiding in this statement. This is a polynomial in x1 through xn of degree d, and it satisfies all this nice stuff. one example that I'll spend a good amount of time on is something called stable polynomials. And also, so included in this is polynomials coming as certain types of determinants of linear matrices. And then another example that we'll see is that some polynomials associated to combinatorial objects called matroids will also sort of fall into this case. I guess we could say something about this class of polynomials, and it could give us information, about, for example, the coefficients of these polynomials or counts of things related to something called matrix.
What is the simplest polynomial
I promise there can be a lot of, so the simplest, so this is excellent, because this is exactly what's my example. So the simplest possible polynomial is to me is just a univariate real rooted polynomial. So let's ignore homogeneous for the moment. Let's just take a polynomial in one variable with real non-positive roots. So the RIs will be non-negative.
The number is out.
Oh, sorry. No. D. And any degree real rooted polynomial with non-positive roots. Then how do I test log? Let's do this log concave. It's just univariate. So I take log of f and I take two derivatives. And I want this to be negative on the positive real line. And so I've written this very conveniently for doing this. So the log turns this product into a sum. I just get a sum 1 to d of minus 1 over x plus r sub x squared. All the roots are less than or equal to 0. So this is in particular defined on the positive real line. And it's less than or equal to 0 on the positive real. So this is at least log concave. And then what happens is if I take a derivative, the roots of f prime have to also be all real, because between any two of these roots, I need a root of the derivative. So the roots of f prime are also real and non-positive. And so f prime, I can write in this form for a different set of real numbers, and I can do the exact same computation. And I will again find that the second derivative of the log is negative. And I can keep doing this and keep taking derivatives. So the same computation gives that f is all derivatives of f are log-concave positive real number. And since there's only one dimension, there's only one direction to go. So all the complexity that's hidden in this definition, I don't have to worry. So to me, this is the simplest example of this. And actually, it's generalizing this to a multivariate setting will give stable polynomials, which is sort of one of the big motivating examples that I want to spend some time on, because I think a lot of this work is sort of motivated by the theory that had already been developed for stable polynomials. So so we'll say that a polynomial is stable whenever I restrict to a line. I'll write it down. Whenever I'm gonna ask that a large family of univariate restrictions are real. So it is real readers. Whenever the direction of my line, v, is in a positive coordinate, and I can take it through any point. Sometimes this is written as that it has no complex zeros. All points whose imaginary parts lie in the positive way. It's not obvious that these two are equivalent, but get bored, you can probably work it out. And so the picture to have in mind for this is if we have, say, a polynomial of degree 4 and 2 variables, and look at the set of points in R2 that make this 0, then what I want so this would be the 0 set for such a thing. Now I take any line, direction B, through any point, W, and I want to hit this only in real points, no contact. So in this example, no matter how I wiggle this line, I always find 4 points. So if we imagine this is degree 4, that's all, there are no hidden complex. And basically using this calculation, we can see that all of these are log-concave. Let's see if I can do this here. Stable. Is that if I imagine taking the Hessian of the log of f, and evaluating at some point. So this is a symmetric matrix, and I want it to be negative semi-definite at this point. So if I evaluate on some vector v, then what is this doing? This is the same as first restricting to the line, starting at t and going in direction v, and then taking 2 derivatives and evaluating it at t equals 0. This is really a univariate thing. And in particular, if p is in the positive ordinate, I claim that this polynomial is real root. Because it's homogeneous, the roots are going to be the reciprocals of what they would be if I had. So I flipped the roles of my direction and going through a point because it's homogeneous. It's fine.
So P is V and V is W.
Yeah. Sorry.
Oh, so V is not necessarily now.
Yeah. I like so. Let's pretend this is W. Maybe that will be better. Yeah. Let's just do it. like, just like you can take derivatives of real-rooted univariate polynomials and you get another real-rooted univariate polynomials, you can do the same thing for directional derivatives in the direction of the positive one.
So in this case, they are also completely the table polynomials are completely wrong.
Yeah, so if f is stable, any directional derivative is stable. Positive orthant. And so you do the same thing, you keep repeating. Means that any stable polynomial is completely log-concave. And again, the reason this is true is the same picture. Is that you take a directional derivative, the roots have to increase. They have to still be real. So this lets us generate a lot of examples. So maybe the other easiest example is just the product of variables. It's not too hard from the definition to see that this is stable. I restrict to any line, real line. I'm going to only have real roots. And then I can also start taking directional derivatives. So for example, if I take the directional derivative with respect to all ones vector, I just sum up the derivatives of that. And this is going to be the n minus first elementary symmetric polynomial. And I could keep taking derivatives. We'll keep getting a stable polynomial. And so in fact, all of the elementary symmetric polynomials are stable. So this up to a constant is going to be the n minus stable elementary symmetric polynomials. So sum over all of the square-free monomials of degree n in this case. Another way to get these, as I said, by taking the determinants.
So before the number, is instead of products of xi, you take linear products of linear functions of the AI with no negative.
Yeah, absolutely. So it's also, you can also multiply two of these together. So some products. Stable polynomial. So for example, if you take, so you take any linear polynomial with non-negative coefficients. It's not too hard to see that that will be stable. And then you can take products of these. Stable, and that's maybe useful for, so Gervitz used this to prove the van der Waals conjecture on doubly stochastic matrices. Yeah, so that's another way to get to generate.
Essentially, is it true to say that any log-concave product of log-concaves is log-concave? Just because the log makes the product sum, and then you
so certainly any product of log-concave polynomials is log-concave, because if you sum up any two concave polynomials, they will be concave. It's non-trivial, but turns out to be true that the product of any completely log-concave polynomials are completely log-concave. That's like a non-trivial thing.
And then the stability is taking it even further.
Yeah, so this is something, this is stronger, but it's a very large sort of useful class, and a lot of the stuff we did for completely log-concave polynomials sort of is motivated by what was already done for these. So I wanted to spend some time. Also, it's a good way of generating lots of nice examples. Other questions?
I'm still not sure why the product of the xi is stable.
Well, you imagine you restrict, let's see, you restrict, so what happens if you take this polynomial and you just restrict it to a line? So that gives you the product TVI plus WI. And the roots of this, roots are just going to be, you just, you get one per factor. Roots are, so minus WI.
Oh, yeah, okay. No, it's been rooted, but it's not, it's not, the roots doesn't lie, you don't know where the roots lie on the line. Because the WI can be, anything.
The WI can be anything, that's true.
The roots can be negative or positive, but you don't care, you just want them to be real rooted.
Yeah.
Okay.
And I guess here, the computation here, you just need around what is here, t equals 0. You need f to be non-zero, and that's enough. Yeah. So you don't necessarily get something with all of whose roots are going to, but it's fine.
Yeah, so I guess in the example above, you didn't really need the roots to be non-negative or non-positive. In the first example, they have a variable one.
Yeah, I mean, in fact.
Right, the roots, I mean, the denominator is positive anyway.
Yeah, so anywhere, in particular, anywhere f is positive, this will be true.
Yeah.
Oh, the second characterization actually makes it very easy to see. The convex one.
For like there it is.
Yeah, for the product.
Right. So sort of a generalization of this, is the determinant of a linear matrix. So A of x, x AI, where the A sub i's are, say, d by d matrices that are either real symmetric or Hermitian, and I want to take them to be positive semi-definite. So all of their eigenvalues to be non-negative. If I took them all to be diagonal, I would be exactly in this situation. And then, if I restrict to a line, I'm restricting this determinant to a line. This is linear, so I'm just going to take T A of B plus A of W. And the important thing is that I'm going to be taking a positive combination of PSD matrices. So unless this polynomial is identically to 0, this is going to be positive definite. And then this is a generalized eigenvalue problem. So if you imagine, if this was straight up the identity matrix, then this is going to be taking the negative of the eigenvalues of this matrix, all of which are real. And it turns out we can replace the identity matrix with any positive definite matrix. So this would be and a sort of important sub-example of this is polynomials coming from graphs. I can associate to it a polynomial whose variables will correspond to the edges of the graph, where I take sum over all the spanning trees. Let's say it's connected, spanning trees. and just take the product of the variables associated to every edge. Sort of a weighted version of the matrix tree theorem, we can write this as a determinant of a linear matrix. Where in front of every variable is going to be a rank 1 positive semi-definite matrix, just a vector times its transpose, sum over all I in E, where these vectors, there's lots of ways to write this, but either, so we treat one of the vertices, the nth, we treat the last vertex differently. So this is equal to n, then it's the difference of 2 coordinate vectors, and the order doesn't matter because we're multiplying it by its transpose, or we just say ei. Yeah. Just for example, take triangle, not the most interesting example, but so then we're going to get a 2 by 2 matrix. In front of x, say 1, 2, we're going to have the vector 1 minus 1 times its transpose, so that's going to contribute x12 minus x12. Then add 1, 3 is going to contribute a matrix 1, 0, 0, 0, 0. 2, 3 is going to contribute a matrix 0, top row 0, 0, bottom row 0, 1. You can check that if you actually write out this determinant, it's the sum. It's like in the elementary symmetric polynomial in these, because this graph is symmetric. You get the sum over all of the spanning trees of the graph.
Yeah, so you want to say this solves a counting problem. If you related it to counting problems in the beginning, so this problem, any weights you put on the edges, it gives you the total.
Yeah, so in particular, if we could evaluate this polynomial at the all ones vector, then we would count the number of spanning trees.
We can.
Which we can, yeah. And if we can, sample from the monomials appearing in F, then we can sample spanning trees from the graph. Okay. One of the other reasons to like these examples is that they have something called negative dependence. The distributions you get have negative dependence. So for example, something showed by Cynthia Vinzant is that if F is stable and has so again, non-negative coefficients, then a certain polynomial you can associate to it. So I'll write down. So you take the derivative, you pick two variables, multiply the derivatives of f, and then subtract off f times the derivative of both. But this polynomial is globally non-negative. In fact, there's certain situations in which the reverse implication holds. So this is very strong, and you get something interesting if you evaluate this at the all ones vector.
It's on R plus n or?
No, globally non-negative. So this is much more than we're in need for what I'm about to say. But so if you imagine you take a polynomial that's where no variable shows up with a power greater than 1. So monomials correspond to subsets. Can associate to this a probability distribution on subsets of 1 through n. Let's say the probability of seeing a particular subset is just, the coefficient divided by the sum of all of them, which I can get by evaluating all ones. Then taking the derivative of the polynomial is equivalent to conditioning. Well, so what is this? So what do we get? If a set doesn't contain your variable, it goes away. And the other ones just survive and the variable goes away. So what we get is we just get a sum of sets containing I, CS. And then just, the remaining variables. And in particular, if you evaluate this at 1, what you get is you get the probability that I belongs to your set. Imagine picking a subset with this probability, then this expression gives me exactly the probability that the element I belongs to my set. And similarly, if I keep taking derivatives, I'm conditioning on larger sets being contained in S. And so then what does this inequality, if I evaluate this inequality at the all ones vector, it gives me something interesting. So take this and evaluate. Then what I get is that the probability. So I sort of divide by f squared. The probability that two elements are in my set is less than it would be if they were independent, if the events are independent. Just as an example, spanning trees of the graph with 5 edges, and I choose a spanning tree uniformly at random. That exactly corresponds to using this polynomial. I could look at, it turns out there are 8 spanning trees of this graph. I could look at the probability that 1 shows up. It turns out that this is in 5 out of 8 of the spanning trees. Look at the probability that 2 shows up in my spanning tree. And 4 out of the 8 spanning trees contain 2. Check. And if I look at the probability that both show up, there's not, I can either add edge 5 or edge 3, right? The probability that both 1 and 2 show up is 2 out of 8, which is less than the product of these. So that's what this says. And it turns out if you want to study distributions with this property, it's and have certain closure properties like conditioning on certain events, then stable polynomials are a very useful way of studying this. So there's a nice paper called Negative Dependence and the Geometry of Polynomials. Then Borchea, Brendan, Liggett. It sort of lays out that if you want negative dependence and closure under some reasonable operations, then this is sort of distribution coming from stable polynomials are the right thing to look at.
So if you continue, because stable derivatives are stable, so what happens if you do it again? You get negative dependence of presence of larger sets in the spanning tree.
Yeah. Yeah, exactly. So you can condition on bigger events.
So if you have any two edges, if you have two pairs of edges, the probability that this pair is in and that pair is in will have the same.
Yeah, so I think the thing, so one way of thinking of this is that the coefficients are submodular, or log submodular. So I think you would get something there. Well, yeah, maybe it's better not to do that. Yeah. That's there's more you can say, but. To sit down. And so then maybe so this also has some nice implications for like combinatorially what the support of such a polynomial can be. And it turns out that this sort of this theory means that there's a nice connection between stable polynomials and something called matroids.
So just before, just one more question about this distribution. So for negatively associated distributions, there are a strong concentration results as for independent distributions. So many of the Chernoff or these strong inequalities hold for negatively associated variables. So you have negative correlations for any subset. So I'm not sure. The reason I asked the question about larger subset, I just wonder whether.
I think these also have negative associations.
So if they do, then you can apply strong concentration.
Yeah, I think and if it's true, it's in this paper.
Okay, good.
I think they're also negatively associated. I always,
it's obvious that that's a limit theory because it's quantitative. It's like this, the Chernoff bound. It's stronger. It tells you that. Anyway.
So I just wanted to. So it turns out there's a nice connection with combinatorial objects called matroids. So I just wanted to spend some time introducing matroids where I haven't seen it. And then maybe after that's done, we can take a break and then get into the meat of the theory. This will be a side on matroids. So a matroid is a combinatorial object. It has a ground set 1 through n, and then something called independent sets, where the independent sets so this is going to be a non-empty collection of subsets. Subsets of n, 1 through n, satisfying two things. One is it's closed under containment. If I have a subset that's independent, and I have an any subset of it, it should also be called independent. And the second is if I have two sets that I'm calling independent, and one is bigger, so T is bigger than S, then I should be able to take some element of T that's not in S and add it to S so that I get something in my collection. I'm going to call the maximal elements of this basis. The maximal with respect to inclusion. And it turns out, so by this second thing, they're all going to have the same size, and that's going to be called the rank. The rank size this way. Maximal element in my set. And what this is doing is this is sort of combinatorially trying to model independence that shows up in various contexts. The most natural of which is linear independence of vectors in a vector space. Take n vectors in a vector space over any field. Then I can take an independent subset can just be subsets of 1 through n that are indexing linearly independent subsets of these vectors. And then my maximal elements will be collections of vectors that are bases for the span. That's the terminology, and the rank will just be the dimension of the span. So for example, if I just pick 4 randomish vectors in R2, then my set of bases, any 2 of them are going to be a basis. So I pick all subsets of size 2 of 1 through 4, that will be the collection of bases of the matrix. And so these are linear. And you can also get these from graphs. So G is a connected graph with n edges. And that's to be, so this will correspond to subsets of edges. If I take my independent sets to be my acyclic subgraphs, collections of edges without any cycles. The maximal ones will be spanning trees. Collections of edges correspond to spanning trees. In this case, the rank will just be the number of the size of any spanning tree, which is the number of vertices. let's say it's my collection of bases would include, 1, 1, 2, 3, 1, 2, 5. Not on matrix kind of this way, but it's a nice way to talk about. It's a nice way to encapsulate sort of these examples with fairly simple combinatorial.
How trivial example is the device polynomial?
Yeah, so algebraic independence and field extensions. Yeah. We can characteristic zero at least all of those are.
Yeah,
so there's lots of equivalent definitions for matroids, and I just wanted to mention one of them that has to do with polytopes. So this was one. There's some is that if you have some, let's say you have some collection of subsets of 1 through n of size d, and you want to know if they're the bases of some matroid. You can do this, so you can look at a polytope and look at its edges. So here's what happened if and only if all the edges of the convex hull of the indicator vectors this is some polytope whose vertices, 0, 1 vertices. And what you need is that all edges are parallel, have a certain direction, parallel to so for example, all subsets of 1 through 4 of size 2 is the octahedron 4 and R4.
So we must the quantifiers there. All edges.
Sorry, for all. No, for some. All edges. If I look at any edge.
Any edge has its particular identity.
Is parallel. Every edge.
Yeah,
sorry.
Not all of them are in the same direction.
Every edge of, I don't know why I erased of, is parallel to ER minus H. Yeah.
And this corresponds to the second action.
Yeah, exactly. So if I pick, so here, this was 1, 2, 1, 3, etc. So if I pick like this edge, I'm subtracting the second coordinate and adding to the third coordinate. So this is going to be parallel to like E2 and E3. And if I pick any other edge, for other edges, I'll get a different difference. But a non-example is actually fairly restricted. So a non-example, if I took just a line segment if I took this line segment, 1, 2, by which I mean 1, 1, 0, 0, 3, 4, by which I mean 0, 0, 1, 1. This edge is bad because I have to subtract 2 and add 2. I subtract from 2 coordinates and I add 2 coordinates. This is
so what is the matroid in the first case?
Well, it's not an edge of the polytope. The second is not an edge of the polytope.
So not, yeah, so this edge is still here, but it's in the interior. It's not a face of the point.
It's not another example, it's just a line segment between two vertices that is not the edge of this polytope, so
Yeah.
you don't expect.
So this is a one-dimensional polytope. So this means that the collection 1, 2, 3, 4 are not the bases of it.
Oh, sorry, you took it. I am sorry, I didn't see that. It's a non-exact, it's a different polytope than the other one. It's just.
Yeah, this is just a. Yeah, I mean, you know, if you had, if this appeared as an edge in some larger polytope, the same thing. But we could also just take this as a polytope.
So.
Yeah. So
what is the polytope of the first one?
this is so this is my collection of subsets. 2, 1, 3, 4. And then
what is the matroid? Sorry, not the polytope.
the matroid. So the bases of the matroid are exactly every collection of subset of size 2 of the numbers 1 through 4.
And that's the basis. So what is the?
And the
so
yeah, and the independent side. If I want to recover the independent sets, I just these are the maximal ones. So I take.
So just take all subsets.
Yeah.
All
So
subsets.
so I would be
So it would be
a set of subsets of 1 through 4, which is the size is illustrated. Yeah, in general, the bases I just collect. I just take closure under containment. I get them. And so if okay, so that's briefly what a matroid is, and then so for a while there was a lot of interest in proving things like negative dependence on the general class of matroids. And so there's interest in understanding sort of, so for example, for the graph example, if I just sum up over all of the bases, the sort of monomial corresponding to that basis, then the polynomial I get is stable. It's exactly the one we wrote down before. And that tells you something about the uniform distribution on spanning trees of graph. And so there was interest in doing this for general matroids. But it didn't work. So not every, some, but not all matroids correspond to stable polynomials.
The correspondence is just sum over all bases. You associate the variable to every element.
Yeah.
The graph.
And even if you were to allow coefficients, so yeah, yeah, exactly what I was doing. So by correspondence, I mean color, you know, sum up over all of the bases, and then there's the product, square free product of variables corresponding to these. And even if I were to allow some coefficients, some non-negative coefficients, so change it from the uniform distribution, it still might fail. But there are explicit examples of matroids, fairly natural matroids for when this fails. So for example, K over then show that the family matroid. Well, is linear over F2. Doesn't, no matter how you try, you cannot find coefficients in this.
What is the dimension? So how many?
So this is a matroid of rank 3 in seven elements.
It's a 7 bases of size 3.
Yeah. And so it's all the non-lines in this picture, where the circle is also a line. So this is, there should be 1, 2, 3, 4, 5, 6, 7 points. It's all the non, so these 3 are on a line, these 3 are on a line. All the not, the bases are all the triples that are not on the line. Yeah, okay, so then probably it's a good time for a break. I spent longer on introduction than I need to, but hopefully now it's all really well motivated. So what's going to happen after the break is that we'll see that this condition of complete log concavity matches up really nicely with the theory of matroids, and that will, we might not be able to get something as strong as negative dependence or association, but we can get something useful. So maybe we should take.
Okay, yeah.
Does it make sense?
Yeah, no, I know a lot of this, but I think it's a fantastic place for everybody. It's just, yeah, it's great.
I realize it's
I'll send people to your recorded lecture. Yeah, oh, that's fantastic.
I realize that we're running it up, but it's very different from the background is very different.
Yeah, it's only, yeah, I think this term is, well, in general, it's challenging to cater to this type of mixed audience. I think in all talks this year, maybe even the locals are more diverse than usual.
Yeah, I mean, there's not a lot of nice. That's nice. Right?
It's nice. It says, yeah, lots of great things about it, but talks, yeah, usually. Yeah, I think we have great talks on Tuesdays for this. Mondays is always, yeah, some people talk to you more than Nima. Even though he worked hard on this, yeah, they did, yeah, really helpful. Yeah, it's really wonderful.
Yeah, Nima always really packs a lot.
He packs a lot, yeah. So he did the introduction was fine, but then he, yeah, well, yeah, it's all natural, and I think it's, yeah, it's what you do. It's yeah.
I'm always very impressed with how much he can pack into.
Yeah, he did want to show what he did above the previous, improvements of the previous works.
Yeah.
So this is Newton polytop. It amazes me. I mean, since I saw it, since I saw Bernstein's theorem, I just, it blew my mind that you can, this gives any information because it doesn't tell you what the coefficients are.
Yeah.
So that's why that's one reason. But you want it's an extension of Bezout's theorem that tells you that you have a system of polynomial equations. You want to know how many solutions they have. Say it's finite, but maximum. So it's 0 dimensional, divided by 0, then what's the maximum number? So okay, Bezout is just basically the product of degrees. What? Yeah. Okay. So that's it can be very tight upper. And Bernstein's theorem says that just takes the I guess so each polynomial has a different concept, and you look at the what do you do? You look at the Minkowski sum of the right, and you
can keep the mixed volume.
Yeah, so it's but basically so each has a mixed volume. Yeah, so the mixed volume is actually evaluated on 1, right? Yeah, so polynomial, when you want the bound of the number of solutions, you just this mixed volume is equal coefficient.
Yeah, I mean, you take this polynomial, which is like Minkowski sum with variable and coefficients, and then it's just a single coefficient in this.
It's like the figure because anyway, you get basically it's a volume of a polynomial.
it's okay.
Yeah, it's some kind of volume of the polytope, which should be much smaller.
Much smaller than the.
Yes, the smaller, yeah. It's more or less the product comes from,
But
when you get the product if each of them is, I guess, a line segment, right? Then you get a cube, you get the product of all the grid of them, right? So let's say there are only two monomials in it, so you get two to the end, but in general, you get the more interesting complex set where you get the bound is much better.
But this is still not strict, right?
Yeah, in general, it's not. Yeah, I think it's very hard to get really well. I mean, so,
Yeah.
I don't think.
But then you're also counting roots in the like not with non-zero points where none of the entries are zero. Like it's points in the tort, like C star to the end.
Yeah, it's also.
I think.
Well,
and so then
I guess
I don't know. I guess he's the expert, but like I've always thought about it as like if you count multiplicities right, then if you look at it in C to the n or projective space, there's some number, and then you want to throw away the right numbers in the coordinate hyperplanes. It's like
so that's
it's still a miracle.
To me, it is. I think, well, to me, since I'm so far from algebraic geometry, so like you said, the right way to write the two theorem with multiplicities, and you get equality actually because you are counting all the low dimensional things. Or basically multiplicities, but even this upper bound, which for us computer science is so discrete math, it's just this upper bound of the product of the grid, which is much easier to prove, is useful enough. And similarly, I guess in the burst sensing, which we don't worry about again the projective or the multiplicities again.
Okay, so now we move on from motivation. And so what I'm going to try and do in the next hour is really give a characterization of this class of, so characterize complete log-concave. And so as a warm-up, I'm going to do this for quadratics. Polynomials are degree 2. It turns out that would actually get us pretty far in doing the whole thing. But so claim that if I polynomial non-negative coefficients degree 2, let's say it's non-zero, then there's a lot of equivalent ways of characterizing it being log-concave on the positive ordinate. So again, equivalently, F is non-positive on a hyperplane orthogonal to its gradient at some point.
But just a second, we want to characterize complete log-concavity. So the polynomial itself has to be log-concave.
Yeah.
So this you can assume. And so all we want is that the first derivative will also have this property. So they are all linear.
And they're all linear with non-negative coefficients. Yeah. So in fact, I could write completely log-concave, and this would be the same. Because it's as long as it has non-negative coefficients, whenever I take a directional derivative, I'll get a linear polynomial with non-negative coefficients, which is stable, which is definitely log-concave. And if I take another derivative, I get 0.
Yeah. So what else do you need? So.
So I need it to be log-concave on the positive one.
Yeah. Okay.
I just wanted to.
Oh, okay, the second is equivalent to the first. Yes,
Yeah.
good, yeah.
So in fact, so this is, it's enough to show that F is non-positive on some hyperplane. And in fact, that's the same as F being stable. So it turns out at degree 2, log-concavity and complete log-concavity and stability are all the same. And the picture to have on mind is we have some here. We have some quadratic form. It's 0 set. It's going to be positive on the positive order. So going to be positive on the positive orient. I want it to be negative on some hyperplane.
This is the origin or the.
And this is the origin.
Yeah.
And this is where F equals, I guess I'm drawing where F is 0. So it's positive in some region that includes the positive orthant because it has non-negative coefficients. And then log-concavity is going to be the same as it being negative on some hyperplane.
When you say hyperplane, you mean through the origin?
Through the origin, yeah. Linear hyperplane. And another, so just to add to this, this means as a quadratic form, it should have only one positive eigenvalue.
In other places, you wrote n is 2, right?
Sorry?
R plus n is R
Oh,
plus
that's
2.
variable.
No, the n is n,
Oh,
but I'm looking only at quadratics.
okay. The degree is 2, but
Yeah. So this is really,
okay, yeah.
the general n. And this really comes from just, I want to at least prove some of this, because it really comes from looking at the Hessian of the log. It really comes from like the definition of log-concavity. Is the Hessian of the log, if you actually write it out, is F times the Hessian of F minus the gradient times its transpose, all divided by F squared. If you actually do out the Hessian, that's what you get. And then if you evaluate at some point, positive orthant, you want this to be negative semi-definite. All eigenvalues negative. And so so if we evaluate this at point, f of a is some positive number, the Hessian of f is a matrix, and then this will give us a vector times its transpose. So this will have rank 1. So we have some matrix, we subtract off a rank 1 matrix, and we get it to be negative semi-definite. That's the situation we're in. In particular, if I evaluate this on a vector orthogonal to the gradient, then this term will just be 0, and up to some positive scalars, I have that the Hessian evaluated. F and A is negative semi-definite on every vector that dots to 0 with the gradient.
And this will be the eigenvalue of the positive. This will be the eigenvector of the positive eigenvalue.
Well, this can vary,
Not
but
necessarily.
yeah. So this is really, I can pick any vector in here and take the orthogonal hyperplane, which should work. It's where you have enough
Right.
in the same direction.
Right.
Yeah.
Because the height,
Yeah. And then, okay, so if you're negative on some hyperplane, then certainly you're, on all these hyperplanes, certainly you're negative on some hyperplane. And so then the only other, and then this implication is one we've already seen. And so the only other sort of implication is that knowing that you're negative on some hyperplane is enough to show that you're stable. And really, from this picture, if you imagine restricting to some line, I'll write it down, but if you restrict to some line in the direction of the positive orth end, then you have to be positive, where, so then you pass through this region where f is positive, but you're also going to have to hit this hyperplane where it's negative. So you have a polynomial of degree 2, and it's positive somewhere and negative somewhere. And so its two roots are going to have to be real. So the only other interesting thing is, and we know that f is positive on the positive percent, and less than equal to 0 h. There's some special cases I want to just ignore here, but so in particular, we pick up a vector in the positive orth end, and any point the line this parametrizes should intersect h. Right? The affine line, maybe it's parallel, but the affine line should intersect h. What we get is f is positive for sort of large enough t, because it's positive at b, but let's ignore the boundary cases and just say negative on h. Since it's only degree 2, that's enough to show that it's real root. We didn't do anything interesting. But then it actually turns out that if you understand quadratics, that actually gets you pretty far along the way to understanding all of them. So then I'm not going to prove is that, so you have degree at least 3, then f is log-concave at some point.
Why doesn't this? Why is this excluding the case of the polynomial having only one
It'd have to be a double. So if you're a polynomial of degree 2 univariate, if you have an honest complex non-real root, you have its conjugate.
Oh, okay.
So as soon as you have one real root, you have.
Yes, so it's either zero.
Yeah. And maybe you have one, but it has to be a double.
No, that's theoretical.
So in some sense, so being log-concave at some point is you can actually write down as it's the same as the directional derivative with respect to that vector being log-concave at that point. But I'm not going to prove this, but basically follows from Euler. You have a homogeneous polynomial, then you sum up xi times the derivative with respect to xi. Yeah, you just get the same polynomial with a factor. And so somehow evaluating somewhere can be translated to just taking directional derivative. Evaluating a point can be translated up to some factors as like taking enough directional derivatives. And so one corollary of this is that this condition that we wrote down with arbitrarily many derivatives, it's enough to actually check the quadratic derivative. So where you take, you pick d minus 2 vectors in R plus to the n and use them as derivative to get down to a quadratic. So this is log-concave for all vectors. Because if you were to take fewer and then evaluate you would get some scalar multiples of what you would get this way, and just take my word for it, the constants would work out. This is still not an entirely tractable definition. But hopefully this gives us hope because we have some condition involving quadratics and we understand quadratics. So I actually want to tell you a much nicer characterization that we can get for these polynomials. I need one definition. We're going to say that a polynomial is decomposable if I can write it as the sum of two polynomials and disjoint variables. And then some collection of variables. H is in the other variables. Both non-zero. And indecomposable otherwise. And I'll just note that if you have a polynomial that's log-concave, then I claim that that implies that it is indecomposable. Because if you could write it in such a way, g within the first k variables is h within the last k variables. If you look at its Hessian, you're just going to get a block diagonal matrix, and there's no way where these have non-negative entries. So this is going to have at least two positive eigenvalues, and so it's going to be positive on a two-dimensional
plane. The log here? The version of the log?
Yeah, so...
And the log kind of mixes.
So this last thing is actually, it's equivalent to a fourth thing, which is that the Hessian of this quadratic has at most one positive. Because there's this really nice relationship between the Hessian of the log and the Hessian of just the polynomial as itself. It can go back and forth on just really small.
So why? So log diagonalization.
So this, the entries of these will be non-negative. So these will, so this will be if we evaluate somewhere positive, but they're pointing to positive worth, then these will be zeros. We'll have a block diagonal matrix whose entries are non-negative. So it's going to have at least two positive values. Whenever you have a matrix with non-negative entries, it has at least one positive value. We're going to pick up one from each. So, I'm not positive. So the main structural theorem we want to talk about is the following. So we start with the homogeneous polynomial with non-negative coefficients. One is that f is completely log-concave.
Yeah, that's very fair.
Yeah.
If that completely log-concave is completely equivalent to the name Lorentzian, but rather than who are you? So that's another name.
Yeah.
Might as well be the same definition.
Yeah. I mean, again, it requires some proof because we define it slightly differently, but it all. So that I'm only going to put 3 things on this list, but the list could actually go on for quite a while. So one is that you can take all of the derivatives, CLC, all I, and that is decomposable. In fact, rather than checking all directional derivatives, here at least we're taking one of the derivatives to be in the coordinate directions, and if you induct on that, you get down to a much more tractable condition, which is that if you take derivatives in the coordinate directions, any way possible to get down to a quadratic. So remember, this is sort of a monomial of derivatives with respect to a variable. But do that as however you can to get down to a quadratic. I want it to be log-concave on the positive quadrant. And you need sort of all the steps along the way, these to be
It's like the only thing that could go wrong is if somewhere in the middle you landed on something which was decomposable.
Yeah. So going from here to here is an induction on the degree. And then this is almost by definition. So this I want to think of sort of the hard and interesting thing. And this is something that we could have hope of actually checking. There's a bunch of quadratics being log-concave is just about the signature of a bunch of matrices. And then indecomposable is really just a question about the support. What coefficients are 0 and not 0.
And it's a finite set as opposed to all the extended.
Yeah. So I want to think of this as sort of an easier, this is the complicated thing we're interested in, this is sort of a tractable way of calculating. In terms of these are the same.
And the decomposability is somehow related to, or decomposability is related to your non-example with the matrix, right?
Yeah, so a non-example, so a non-example of this, are decomposable. So x1, x2, x3, x4 is a decomposable polynomial because I've written it as a sum of 2 polynomials in disjoint sets.
Newton polytope is this segment.
Yeah, and the Newton polytope is also a sort of non-neutral. Yeah. Another way to think about this, this down. There's another nice way to think about this, but I'll get to in a second. So I wanted to, so the interesting part of this proof is going from directional derivatives to a coordinate. And the proof is actually not that bad, so I wanted to try and give it. That's the goal. Do the statements make sense? The statements are more important. Okay. Okay, so I need a quick lemma in order to do this. Is that a condition under which you can add two completely log-concave polynomials and get a completely log-concave? Is so there. F, G, or completely log-concave, and some derivative of F, some directional derivative of F equals some possibly different directional derivative of G, non-zero, negative vectors. Then the sum. This, if you can manage to find two directional derivatives that are the same, which is a pretty strong condition, then you're allowed to add. You're allowed to add these two. And so the sketch of the proof is that if you imagine that F and G are quadratic, then this is going to give a common hyperplane on which they're negative. So we're going to have F and G being positive origin, and then F and G are going to be negative or non-positive. And the gradient of F curved, which is going to equal the gradient of G at this other point. It's going to give us a common hyperplane. Positive. So in particular, if you add them, both of these, the sum will also satisfy this, right? Well, you add two positive things, they're positive. If you add two non-positive things, they're non-positive. So F plus G is also non-positive on this hyperplane. We said it still has non-negative coefficients, and so that's enough to show that it's log-concave.
You could take any positive combination.
Yeah, any positive combination. That's true. If it's quadratic, then
Yeah.
And the thing I'm about to erase just says that you can get away with considering. Okay. And so this is actually going to be enough to prove so we're going to assume that all the derivatives are completely log-concave and that F is D. Actually, another nice way of saying in that F is decomposable is that if you took a graph on your vertices 1 through n with if you put an edge between I and j, if x of I and x of j show up in a common denominator. In particular, if the derivative with respect to both is not identically but this graph is connected. But that's, you can't partition the vertices into two sets that don't interact.
That's exactly otherwise it's decomposable.
Yeah, but here, here I would draw this graph. 1, 2, 3, 4. It's another way of writing this. And so in particular, what I'm going to do is I'm going to reorder the vertices so that I'll reorder so that all sort of truncations I and j are say less than some value k. And this graph is connected. And then I claim that knowing that all of the partials of f are CLC is enough to show that positive linear combinations of them are CLC. Okay. In particular, if I go all the way up to n, then I'm recovering a directional derivative. And that will be enough to finish everything. Basically, we can just induct on k, is the reason I've written it this way. For k equals 1, I'm not doing anything. And otherwise, I can partition my vector coefficients. These will be non-negative vectors. If I assume that C and C are plus. And the derivative derivative A with respect to this polynomial equals the derivative of B with respect to this polynomial, and they're the same. C I, C k minus 1, I. These will all be positive, and the assumption is that at least one of these is non-zero. This will not be 0. That's what this does. And so this exactly gets me into this position for this lemma. So what I'm going to do is I'm allowed to add this polynomial to this polynomial, and I'll get something sort of by induction. These are already completely log-concave, and I'm allowed to add them. And that's exactly the k plus 1 polynomial. And so this lemma allows me to go from finitely many derivatives just with respect to coordinate directions to any positive linear combination. So if you keep doing that, then you get to, and you induct on you induct in all the ways, the degree and the degree, then you get to complete log-concave.
I have a question about the decomposability. Obviously, it's basic dependent. It depends on the names of the variables.
Yeah.
But we said when you gave examples that if you took linear combinations of variables At least when we talk about product of
Yeah.
variables. So if we change basis with a non-negative matrix, right? Full rank. So I rename the axis.
Yeah.
It preserves complete log-concavity, or you need to also define it with respect to a different order?
Yeah, it should preserve complete log-concavity.
With respect to the
new,
order.
Yeah, if you need to map one positive ortho, like if
You
you're
need
changing
to
variables.
map the orthos, okay? Because when we did it for product of variables, we didn't need to change the order.
Yeah, even if you take products of linear forms,
Yeah.
you could, so it's still stable or completely log-concave with respect to the
Original.
but
Yeah.
you could consider it with respect to sort of the
I
larger.
don't want to move to a different. But I'm asking whether in this generality I'm allowed to change
I see.
my positive linear transformation. I mean, all the entries are non-negative.
Yeah.
And if you remain completely non-concave with respect to the original positive order.
Yeah, you should be. You can, because if you do sort of a positive linear transformation, then taking the derivative with respect to a variable will translate to taking a positive direction.
Positive direction. Okay,
Yeah.
good. Yeah.
So I guess it's more clear using the first definition. But then by this theorem, it also has to feature here. Yeah. I mean, everything here is very basis dependent. Because we're doing.
But not this. I mean, you could change.
Yeah.
That's also not
okay.
I mean, it's just somehow it's far from being clear that when you change basis, the notion of composability or connectedness doesn't change, right?
Yeah.
But it doesn't.
Yeah. I mean, this is. I guess I think of this as the stronger condition than this one.
I understand, but I mean, you could imagine taking x1, x2 plus x3, x4, which is decomposable, changing basis in a positive way when you get something. But you cannot. Well, you need the directional derivative condition. But
you could certainly do a change of basis, and it would be dense.
Exactly.
Yeah.
Like a random change, but then
But then this will.
Yeah, this will not help.
Yeah, I think this is sort of the stronger. This is really just about the support, which could change drastically if you do a change of coordinates. But this one is.
Yeah, but I'm thinking of condition 2. In condition 2, you have the decomposability condition, right?
Yeah.
In condition 2, you could change the basis that destroy the meaning of decomposability, but then you also do this.
Yeah, you still need the,
Yeah, exactly. Okay, good.
And there are also other issues if you change basis, right? R plus to the n changes and the non-negative coefficients change. I mean.
Yeah, so I guess I was talking about doing sort of a positive, like being careful with the linear transformations that you allow. Like you have to map the positive orthon into the positive orthon. Or like where the matrix representing your transformation has all non-negative entries. Then it's okay. Okay, I guess I should think about finishing up, huh? Well.
Yeah,
Okay.
That kind of totally good.
So, let me just give a few nice consequences of this. So one consequence of this, so if someone hands you a polynomial and asks you to check if it's completely log-concave, most likely this third thing is the thing you should use to check. And so in particular, it turns out that for any matroid, the basis generating polynomial if all coefficients equal to 1, will be completely log-concave. And a sort of related polynomial you could write down for independent sets. You sort of need to homogenize with an extra variable. Both of these are completely log-concave. And maybe I'll at least give you an idea of the proof of this one. The indecomposability is not too hard to just check straight from the axioms. And then if you want to check,
What's the ones? Do you assume that the polytop of the matroid is connected or something like that?
well, I assume it's a matrix.
Yeah, it will follow from that.
It will solve from
Yeah, forget the just the definition of what the matroid is, guarantees is connected.
It's the thing that you can always add.
Yeah, that you can switch between two independent ones by adding one.
Yeah, it's not 100% obvious, but it's not too bad to just check. And then if you want to check so I'd say let's not worry about this one. And if we want to check this, then we imagine if we take derivatives with respect to a polynomial, these are going to be 0 if any variable is greater than 1. So we're taking any derivatives twice. Because, yeah. And so then we can consider just indicator vectors of some subset of variables. And just like before, if we imagine taking the derivatives with respect to this is going to be the sum for all bases that contain that subset. And in fact, this is sort of the basis generating polynomial of another matroid called the contraction. So this will be another matroid polynomial. Except here, all of the bases will only have size 2 because it's quadratic. Because that's how many derivatives I'm taking.
You took alpha to be 1 and s, so now you take s.
S of size t minus 2.
Okay.
The point is that I can get away with just checking quadratics. And so it turns out that matroids of rank 2 are not that interesting. There's not so many possibilities. So 1s has rank 2. You imagine linear independence of vectors in a 2-dimensional vector space. Then it actually defines an equivalence relation on the elements where I and j are not a basis for, say, this contraction. Equivalence relation. Either, you imagine. Yeah, exactly. Parallel or not. And so then up to some relabeling, if we were to write down the Hessian of this thing, we're going to get, and we partition using the equivalence classes, we're going to get a bunch of zeros, and then the rest is going to be ones.
If you make them all equal, these equivalent classes, then it would be just general position.
Yeah. And then this would just be, these blocks would have size 1. And this is the all ones matrix, which is rank 1, minus positive definite matrix. And so in particular, this is going to be negative semi-definite on the orthogonal complement of this. So this is negative semi-definite on the hyperplane sum of the coordinates.
This is different only if I took any family of sets D.
Yeah.
And if I have a point, yeah. That's the only case for that. I mean, if I took it will characterize matrix.
Yeah, yeah. And in addition to this, if you have some polynomial, and let's say it's homogeneous, multi-affine, and this is log-concave, it actually implies that the support of that are the bases of the set of bases of Q. It really is just sort of spot on characterizing these Matroids. And yeah, maybe I would say one of the slick corollaries of this actually comes from considering the independent set polynomial, which is slightly more involved, but not much more involved than this. Is that it becomes interesting if you restrict, if you do sort of a change of coordinates, like Avi was suggesting, is that if you take all the x sub I variables and set them equal to each other, you get it as a polynomial degree 2. And its coefficients will count the independent sets of a certain size. So you get a polynomial of degree n, x to the k, and y to the n minus k. And its coefficient is exactly going to be the number of independent sets of size k. Just from this formula. And this is also completely log-concave. And so if you actually work it out, you can get interesting inequalities using this. In particular, you take, I'm allowed to take, if I take the derivative with respect to x, say k minus 1 times, and the derivative with respect to y, n minus k minus 1 times. This will be a quadratic. It will be a log-concave, it'll 2 by 2 matrix. It'll have one positive eigenvalue and one negative eigenvalue, necessarily. And so its determinant, will be less than 0. And if you actually work out what this does, it takes derivatives from one side and takes derivatives from the other side. And there's only going to be 3 coefficients remaining. And if you actually keep track of what the scalars do, this will give you this will. It'll give you Newton's inequalities for this polynomial. It'll say something about the number of independent sets. It'll say the sequence of sort of keeping track of the size of the number of independent sets of a given size is sometimes it's called ultra log-concave. And this was something that had been open for several decades. This was known as Mason's conjecture. And various incarnations of this have been sort of proved over the last few years using techniques sort of related to this.
You're possibly missing a square. You're possibly missing a square in what you just wrote on the left-hand side. It's weird.
Can you speak a little
What
louder?
you're missing is clear on the left-hand side.
Oh, yeah,
On
yeah,
the left hand.
yeah, thank you.
Perfect.
Yeah, so that it's true, yeah. Yeah, great. And so one thing this can, and so this sort of suggests one thing this is useful for is if you want to show ultra log concavity of some discrete sequence, one way of doing that is cooking up some multivariate polynomial and showing that it's completely log concave. And then using some nice, and then you know that restrictions or maybe some other transformations of the polynomial will have this property, and from that you'll get a sort of discrete log concavity of coefficients. That's sort of one thing this can be used for. And then, so next week, I'll say that it can be used for other things as well. But so this is some nice class of polynomials. It includes a lot of interesting and important examples. It can be characterized fairly concretely. It's good for showing sort of discrete log concavity of coefficients. And then next time we'll see it's also good for some sampling applications also. So thanks for your time.
All right. So questions to Cynthia. I hope you have. Anybody? I always have questions, but okay. So yeah, just historical question. Matroids have been around since I don't know McLean. I don't know it was the first part of the past century.
Yeah.
Nobody connected it to polynomials. Just people wrote massive things on Matroids. Nobody connected it to this polynomial, this analytic side until this decade.
I guess that's a good question. So to me, the main stuff that I know about is this sort of stable polynomial connection with Matroids, which really took off in sort of the early 2000s.
You're talking about the McPherson domestic.
No, the work of Brendan.
Yeah, so,
yeah,
but when is this other thing is probably even earlier, the connection to the Newton polynomial, but that's not analytic, it's not quite.
Yeah.
So Peter.
Yeah, I think, I don't know when people started thinking about it, but he sort of cracked it open in like the early 2000s, I think. Probably people were sort of thinking about it before then, but I don't know exactly when it started. I mean, for the graph, the graph polynomial, like the spanning tree polynomial, I think it goes back to like Kirchhoff.
Yeah, but it's not clear that it's that it's a property of Matroids. It's just spanning tree.
Yeah.
Spanning tree is very special. I'm talking about general Matroids related in this way, or related at all to stable or log-concave polynomials. So that's what that.
Yeah, I mostly associate it with sort of work of Peter Brendan in sort of the early 2000s, but I think that's when it was most active. I don't know when it sort of.
Matroids were active for I don't know 70 years before.
Yeah, but yeah, Peter did a lot of work on stable polynomial. Like had a lot of breakthroughs on this in this theory in sort of the early 2000s.
But that's this connection with the discrete object to this analytic. Okay.
Yeah.
That's what I was wondering. More questions to Cynthia. Okay.
Okay.
Thanks.
Thanks.
Great.